Ever wondered about the invisible glue holding the universe together? We're diving into something super basic that's been hiding in plain sight for decades, right under the noses of the smartest scientists out there. Today, we're diving into the story of a quiet, determined physicist who unveiled this cosmic secret. James Chadwick, the man who discovered the neutron. Our story starts in the early 20th century, a time of electrifying discovery in physics. Scientists like Rutherford had just figured out that atoms weren't tiny, indivisible balls. Instead, they had a dense, positively charged core called the nucleus, with negatively charged electrons whizzing around it. But this model had a major problem. Let's take helium, for example. Its nucleus has a charge of +2, which means it has 2 protons. Simple enough, right? But here's the catch. The mass of the helium nucleus was known to be about 4 times the mass of a single proton. So, where was the extra mass coming from? 2 protons should only have a mass of 2. What was making up the other half? For a while, physicists had a workaround theory. They thought the nucleus must contain extra protons to account for the mass, but also some electrons tucked inside to cancel out the extra positive charge. So for helium, they imagined 4 protons and 2 nuclear electrons. This balanced the books, making the charge +2 and the mass about 4. It seemed plausible, but it was a clunky solution that created more problems than it solved, especially with what they were learning about quantum mechanics. The idea of an electron, which is incredibly tiny and zippy, being confined within the even tinier nucleus just didn't sit right. It was like trying to fit a race car in a shoebox. This is where our hero James Chadwick enters the picture. Born in 1891 in a small town in England, Chadwick was a student of the great Ernest Rutherford, the very man who discovered the atomic nucleus. Chadwick was known for his patience, his meticulous experimental skills, and his quiet persistence. He wasn't flashy, but he was brilliant. Rutherford himself had suspected something was up. As early as 1920, he proposed the existence of a neutral particle, a sort of proton-electron combo that would have mass but no charge. He even coined a name for it, the neutron. But proving it existed was another matter entirely. How do you detect something that has no charge? Most particle detectors work by spotting the electrical trail a charged particle leaves behind. A neutral particle would just ghost right through, completely unseen. It was a scientific ghost hunt. For over a decade, the mystery of the missing mass and the search for this elusive neutron lingered. The puzzle pieces were scattered across labs in Europe. In Germany, 2 physicists, Bose and Becker, were bombarding the light element beryllium with alpha particles. Those are the helium nuclei we talked about earlier. They noticed that this process produced a new, incredibly penetrating form of radiation. It was so powerful it could pass through several centimeters of lead. They thought it might be a type of high-energy gamma ray, but something about it was off. Then, the story moves to Paris. Irene Joliot Curie, the daughter of the legendary Marie Curie, and her husband Frederick Joliot, decided to investigate this strange new radiation. They performed a clever experiment. They aimed this mysterious beam at a block of paraffin wax, which is rich in hydrogen atoms. And what they saw was astounding. Protons came flying out of the wax with incredible energy. This was a huge clue, but the Joliot Curies misinterpreted it. To explain how gamma rays could knock out protons with such force, they would have to possess an impossibly high amount of energy, violating the known laws of physics regarding conservation of energy and momentum. It was like a ping-pong ball knocking over a bowling pin. Something wasn't right. When Chadwick, back in Cambridge, read their paper, his scientific intuition went into overdrive. He reportedly said, "I do not believe it." He knew that a massless photon, a gamma ray, couldn't possibly pack enough punch to send a heavy proton flying like that. But what if the mysterious radiation wasn't radiation at all? What if it was a particle? A particle with mass, but no charge. Rutherford's neutron. This was Chadwick's moment. He realized that a neutron, being electrically neutral, but having a mass similar to a proton, would be the perfect billiard ball to knock a proton out of the wax. It was a head-on collision between two particles of nearly equal mass. This explained the high energy of the ejected protons perfectly, without breaking any laws of physics. Chadwick knew he had to act fast. He dropped everything and dedicated himself to proving his hypothesis, working almost non-stop for 10 intense days and nights. He recreated the experiments from Germany and France, but with his own ingenious twist. He used a more sophisticated detector, an ionization chamber, to precisely measure the energy of the particles being knocked out of various materials. He didn't just use paraffin wax. He aimed the beryllium radiation at other elements too, like nitrogen. He meticulously measured the recoil of the different atomic nuclei. His calculations showed, again and again, that the results could only be explained if the incoming radiation was actually a stream of neutral particles, each with a mass almost identical to that of a proton. In February 1932, Chadwick published his groundbreaking paper, modestly titled Possible Existence of a Neutron. Soon after, he submitted a more definitive paper, The Existence of a Neutron. The ghost had been caught. The scientific community was electrified. The discovery was elegant, conclusive, and it changed everything. The discovery of the neutron was a monumental turning point. It solved the mystery of the missing mass in the nucleus in an instant. The atomic model was revised. The helium nucleus wasn't 4 protons and 2 electrons anymore. It was 2 protons and 2 neutrons. The mass was 4. The charge was 2. It was perfect. It was simple. It was correct. Chadwick's discovery didn't just tidy up our picture of the atom. It unlocked a new and terrifying power. Because neutrons have no charge, they aren't repelled by the positive charge of the atomic nucleus. This means they can slip right into the heart of an atom with ease. While a positively charged proton would be pushed away, a neutron is the perfect projectile to probe and even split the nucleus. This realization paved the way for the discovery of nuclear fission. Just a few years later, scientists found that bombarding uranium atoms with neutrons could cause them to split, releasing a tremendous amount of energy and, crucially, more neutrons. This set off a chain reaction, the fundamental principle behind both nuclear power and the atomic bomb. Chadwick himself was deeply involved in the subsequent developments. As World War II loomed, he became a key figure in the British efforts to develop an atomic weapon. He was awarded the Nobel Prize in Physics in 1935 for his discovery, a well-deserved honor for a decade of persistent, brilliant work. So the next time you think about the building blocks of our world, don't just think of protons and electrons. Remember the quiet hero of the story, the neutron, and the patient scientist who found it. James Chadwick's discovery wasn't just about finding a new particle. It was about solving a deep cosmic puzzle, and in the process, changing the course of human history forever. It shows how one person's relentless pursuit of the truth, driven by curiosity and a healthy dose of skepticism, can light up the darkest corners of our world. Thanks so much for watching. If you enjoyed this journey into the heart of the atom, don't forget to hit that like button, subscribe for more stories from the history of science, and ring that notification bell. Let me know in the comments what other scientific discoveries you'd like to explore. See you in the next video.